Hi, I'm going to introduce on improving deep learning trace analysis with system call arguments, which is a work by Daniel Aloïse, Sayed Vaid Azari, François Tétrault, and myself, Quentin Fournier. So first of all, what is a trace? So a kernel trace is a sequence of low-level events called system calls. So below you have an examples of 4 events, the first 2 corresponding to the system call read, generated by Firefox, and the last 2 corresponding to the system call getTID, generated by DOM Worker. And so traces are helpful to detect latency, bug, intrusion, and have been extensively used in the literature. However, most of the current methods only rely on the system call names. So in the example below, we would only consider read and getTID. However, all the arguments are already available or can be made available quite easily. So we could consider the process names, the PID, the TID, and so forth. And we argue that considering additional information should improve the model, and especially it has been shown that neural networks performance improve with the amount of information considered. So for certain arguments, we are going to learn an embedding, which is a real value representation that encodes the meaning of a word. So for example, for a process named Firefox, we would learn a vector. And for other arguments, we are going to apply an encoding, which is a predefined deterministic transformation of a numerical value. So for example, for a TID of 1905, we could apply a cosine function and get an encoding of 0.367. So for the actual encoding, we will refer you to the paper. Once we have a numerical representation of the arguments, we can either concatenate them or add them together. And so using embedding, encoding, concatenation, and addition, we are able to learn a representation of the system calls with their arguments. So here you have the computational graphs that allows to learn such representation. So in blue, you have the arguments or the information rather considered. So you have the system call name, entry or exit, the return value, the process name, PID, TID, and the timestamp. In green, you have the embeddings that we learn, and in white, the transformation that does not require any parameters. So PE stands for the encoding, and you have the addition and the concatenation. And so this is the way that we consider the arguments. So to evaluate our approach, we use 2 different neural networks, the LSTM, which is the most commonly used for traces, and the transformer, the current state of the art for sequences. 2 different objectives, the left-right language model, which has been used to detect anomalies and especially intrusion detection, and the mass language model, which is often used to pre-train model and improve performance on the downstream task. And we consider 2 datasets. Because no large dataset was publicly available with the system call arguments, we generated one ourselves and made it public. And to validate our results, we evaluated our approach on a second dataset collected by Siena, our partnering company. However, this dataset is private. I'm going to conclude by going over the result quickly. So here we compare the accuracy for the different models, objective, and dataset. So in gray, you have the accuracies when no arguments are considered, such as in the literature, and in orange with our proposed approach to consider the argument. So considering the argument consistently improves the performance, sometimes slightly, but sometimes by up to 11%. And we argue that this applies to any models and any dataset of traces. So if you have any question, I would gladly answer after this video. Thank you.